today we are going to focus in on our synthesis and decomposition reactions. So our goal for today is that we'll be able to recognize and predict the products of synthesis and decomposition reactions. Okay, so let's go ahead and focus on synthesis reactions first. So we discussed yesterday that synthesis, that is kind of synonymous to making something, okay? So to recognize a synthesis reaction, what we're going to see is we are going to see two elements as our reactants. And these two elements, they're going to combine to form a compound. Okay, so just kind of generally looking at this, we would have two elements, A plus B, that then combine to form some compound A, B. Okay, something to keep in mind here when you guys are writing the product. Okay, so your product must include all elements. Okay, because we know conservation of matter, we can't go destroying some of our particles. So that product must include all the elements. We also need to keep in mind that we know when we write a chemical formula, we need to balance our charges. Okay, so our product needs to have balanced charges. Okay, what that means is when we look at these two elements, we're going to have to see what charge each one has individually and see what we need to do then to balance them out. Okay, so let's say, as an example, we have aluminum plus oxygen. Oxygen is one of our diatomic gases, so whenever it's by itself, we're going to have two. Okay, so this is a synthesis reaction because we have two elements by themselves. When we form the product, okay, these two elements are going to come together to form our compound. So we'll have a compound with aluminum and oxygen. It's not enough just to say ALO, because we need to show what that formula is going to be so that our charge is balanced. We know looking at aluminum on the periodic table, aluminum typically has a charge of +3. Oxygen typically has a charge of -2. Okay? So we need this +3 and -2 charge to balance out. Okay? So we know 3 and 2 both go into 6. So in order to get that, we would need 2 of our +3 aluminums and 3 of our -2 oxygen. Okay? The formula for this product then ends up being Al2O3. Something to notice here is that your subscripts from the reactants do not carry over. Okay, so notice how in our reactants, oxygen, we had O2, and now in our products, it's O3. Okay, the subscript in that product is totally dependent on the charges. Okay, we are not just going to carry over those subscripts from our reactants. We need to look at those individual charges and think, what do we need to do in order for them to balance out? Okay, so we know once we get here, now we need to balance out that reaction. So if we look, our oxygens, these guys are going to kind of be the tricky one because we have 2 on a reactant side and 3 on our product side. So in order to have an equal number on each side, we're going to need 3 O2s. So that way we have a total of 6 oxygens as our reactants. And that means we would need 2 of these Al2O3s because if we have O3 2 times, we again end up with 6 oxygens. Okay, so then looking at our aluminums on our product side, we have 4 aluminums, which means we also need 4 aluminums on our reactant side. So we need 4 Al. Okay. So to recognize the synthesis reaction, we are going to see 2 elements by themselves. Okay. And these 2 elements are then going to combine to form one product. And when we write that product, we have to make sure our charge is balanced. Okay. Let's look at another example. Magnesium reacts with nitrogen. Okay. So we know magnesium, that's just going to be Mg plus nitrogen. That's one of our diatomics. So when it's by itself, it's going to be N2. Okay. Again, we know this is a synthesis reaction because we have two individual elements by themselves. They are going to react to form one compound. So to figure out what the formula for that compound is going to be, again, I cannot just carry over those subscripts. I need to include both elements, our magnesium and our nitrogen, and I need to make sure my charge is balanced. So I know magnesium, that typically has a +2 charge. Nitrogen's typically -3. So for this to balance, okay, I need my +1 and -3 to balance out. I know they both go into 6. So in order for that to balance, I need 3 of my +2 magnesiums, so you get an overall charge of +6. And I need 2 of my -3 nitrogens to get an overall charge -6. Here my positive and my negative charge balance out. Okay. So again, I cannot just carry over the subscripts. I have to look at my individual charges to write that formula. Now I just have to balance. I have 2 nitrogens on my reactant side, 2 nitrogens on my product side. So that one's good to go. I have 3 magnesiums on my product side, so I need 3 magnesiums as my reactants again. Because remember, however many particles I start with, that's how many particles I need to end with. Look at our decomposition reactions. Okay, so unlike synthesis and a decomposition reaction, like we've already kind of talked about, here we have a single compound as our reactant. That compound is then going to decompose or break down into something simpler. So a single compound as a reactant that breaks down or decomposes into simpler substances. Okay, so just in general, if we have our compound AB, when we decompose, it's going to go into components A and B. So let's look at a simple one first. Let's say we have the formula K2O, or the compound K2O. Our only reactant, so we know this is going to be decomposition. It's going to break down into its individual components. So if we have potassium and oxygen, when K2O decomposes, it's going to break down into potassium and oxygen. And we know oxygen's diatomic, so when it's by itself, it's going to be O2. Again, notice how we do not just carry over the subscripts. We need to think, what is potassium by itself? It's just K. What is oxygen by itself? That's our O2. Okay, so we have a compound breaking down into something simpler. Okay, so now to balance, we have 2 oxygens on our product side, which means we also need 2 oxygens on our reactant side. That means we are going to need 2 K2Os. So now if we have K2 2 times, that means we're going to have 4 potassiums. We also need 4 potassiums. Okay, so that was a nice example of a decomposition. You just have one compound with 2 individual elements that's then going to break up into those individual elements. We are going to see some that are a little bit trickier where we're going to have to know the rules. And you guys will be given these rules on quizzes and tests. 5 main types here. Okay, and again, you guys will be always given these on quizzes and tests, so you don't need to memorize these. Okay, but binary compounds, that's just when we have 2 elements. That is like what we saw up here. These guys are going to break into their 2 individual elements. The example that we looked at earlier where we just had 2 elements in our compound, potassium and oxygen, that decomposes into elemental potassium and elemental oxygen. That's going to be an example of our binary compound. So just 2 elements in that compound breaks apart into those 2 individual elements. Okay. Our next example is going to be for a carbonate. Okay, and carbonate, that's going to be one of our polyatomic ions, CaO3. Or sorry, carbonate, that's just going to be CO3. So whenever you guys see a CO3 decomposing or a carbonate, that's always going to decompose into CO2 and a metal oxide. So if we look at an example of this, okay, we could have calcium carbonate, so CaCO3. Okay, when this decomposes, it is going to decompose into CO2. So we know CO2 is always going to be one of our products and a metal oxide. So we're going to have to look and see who is our metal here. And we're going to see that our metal, that's our calcium. Okay. Our calcium, our metal, is then going to bond with our oxygen. Okay, that's our metal oxide. So we have CO2 and our metal bonded to oxygen. Make sure you guys write, when you write the formula for that metal oxide, you balance your charges. Okay, so calcium, this guy has a +2 charge. Oxygen, this guy's -2. So it ends up balancing on its own. So calcium oxide, that is just CaO. And when we check to make sure this is balanced, we have 1 calcium on either side, 1 carbon on either side, and 3 oxygen. Okay, so this one is good to go. We got lucky. Okay. The second type that we're going to look at is when a hydroxide decomposes. Hydroxide, that's another one of our polyatomic ions. This is when we see a compound with an OH. Okay. This guy is going to decompose into H2O. So H2O is always one of our products, and again, a metal oxide. So our metal bonded to oxygen. Okay. So let's say we have sodium hydroxide, NaOH. Since we have a hydroxide, when this decomposes, one of our products is always going to be water. So we know it's going to be H2O. And our other product is going to be a metal oxide. So looking at our sodium hydroxide, our metal here, that's our sodium. So our sodium, that is going to bond with our oxygen. Okay? And just like before, we need to make sure our charge is balanced. So sodium, looking at the periodic table, that one's typically +1. Oxygen is typically -2. So in order for these to balance, we're going to need 2 of my +1 sodium. Okay, so my formula for that sodium oxide can be Na2O. Okay, so then in order for this to balance, okay, our equation then, we have 2 sodiums on our product side. That means I need 2 sodiums on my reactant side. Okay. Now I have 2 oxygens on my reactant side, and I also have 2 on my product side. So my oxygens are good to go. And likewise, I have 2 hydrogens in my reactants and 2 hydrogens in my product. So this one is balanced. Okay. The main idea, when you have a hydroxide, some metal bonded to OH, when that decomposes, you're always going to get water, H2O and Na2O. All right. So our next type, this is going to be our chlorate. Okay, so chlorate, another polyatomic ion. This is going to be ClO3. Whenever you see ClO3 decomposing, it's going to decompose into O2, so oxygen and a metal bonded to chlorine, a metal chloride. Okay. So let's look at an example of this guy. Let's say we have potassium chlorate, KClO3. Okay, +1 -1, charge is balanced. Since we have a chlorate decomposing, we always know one of our products is going to be O2. Okay, and a metal chloride. So we're also going to have our metal, looking at our formula, that's our potassium, bonded to our chlorine. Okay, that's our metal chloride. Here, since potassium's +1 and chlorine's -1, that formula is already balanced. Okay, so whenever you have a chlorate, you see that ClO3. That's your only reactant. That's going to decompose into oxygen and a metal bonded to chlorine. So now that we have our formulas for our products, we can go ahead and balance our equation. We can look and see the oxygen. That's the one that's different on either side. So on my reactant side, I have 3 oxygen. On my product side, I only have 2. So if we need those to balance one another out, we know 3 and 2 both go into 6. So in order to have equal amounts on either side, we're going to need 2 my KClO3s and 3 O2s. Because now I have 6 oxygens on either side. And now I have 2 potassium and 2 chlorine on my reactant side, so I also need 2 potassium and 2 chlorine on my product side. Okay. The main idea there, whenever you have a chlorate that's ClO3 decomposing, you're always going to get oxygen and potassium chloride. Okay. So then my last one that we're going to look at is acids. And we haven't talked about acids much, but the way to recognize an acid is you have this hydrogen in front. Okay, so if you see a hydrogen in front of a element, okay, that's going to tell you that you are an acid. Okay, so we are talking about non-binary acids. So that means we have more than just 2 elements, because if we only had 2 elements, then that would be a binary compound. Okay, but if we have an acid that's non-binary or with a polyatomic ion, that's H plus a polyatomic ion, then we're always going to decompose into water and a non-metal oxide. Okay. So for an example of this, we could have H2SO4. Okay, so notice how we have that hydrogen out front followed by a polyatomic ion. When that decomposes, we're always going to break down into water. We're always going to get H2O. Okay, so that's always going to be one of our products. We're also going to get a non-metal oxide. That means a non-metal bonded to oxygen. So looking at this, our other non-metal here is going to be sulfur. So we're going to have sulfur bonded to oxygen here. Unfortunately, with our non-metals, they're going to form a covalent compound. So we can't write out our formula by looking at the charges. So to figure out what the formula for this non-metal oxide is going to be, we're going to make it easier on ourselves. We're going to say if I have 4 oxygens on my reactant side, I need 4 oxygens on my product side. In my H2O, I already have 1 oxygen, which means I need 3 in my non-metal oxide. Okay, so this is the only time when you guys do not need to look at charges to balance out that formula of your product. The only time when you do not need to look at those individual charges. When an acid with a polyatomic ion is decomposing, to figure out the formula for that non-metal oxide, so that non-metal bonded to oxygen, just look to see how many oxygens you have left over from that reactant side once you already use 1 to make H2O. So if we start out with 4 oxygens, we used 1 to make water, that left us 3 to bond to that non-metal. Okay. So that is the only time when you guys do not need to look at your individual charges. Okay. All right. So there are our synthesis and decomposition reactions. As a reminder, synthesis, this is when we have 2 elements combining to form 1 compound. Okay, so we'll recognize this when we have 2 individual elements as our reactants. And then when we write the formula for a compound, we need to look at those individual charges. Okay, so like in this formula, aluminum was +3, oxygen was -2. We needed to balance those charges in order to get the formula for our product. Okay. And the big thing there is subscripts do not carry over. Okay, so we need to look at those charges. That's different than decomposition, because in decomposition, we're going to have a single compound as our reactant. So when we're recognizing this, we'll see that 1 compound as a reactant that's then going to break down according to these decomposition rules. Okay, and again, you guys will always be given that on quizzes and tests, so you do not need to memorize that. All right, let me know if you have any questions. Otherwise, have a fabulous day.